Hi everyone, I'm Isma and welcome back to the channel. Hope you guys are doing great. This is the second day of our lecture series, Let's Learn Quantum Computing from Scratch. And this video is going to be the second part of our first lecture. But before proceeding with our today's lecture, let's just have a brief recap of what we did in the last part. So in the last part, we were talking about coins and dice, and we were performing the experiments where we were flipping the coins and rolling the dice, and then we wanted to see that how many total states do we get. We also saw in the last video that when we increased the number of coins and the number of dice, the total number of states also increased. And in the end, we also saw that the general expression that described the way that described the sequence with which these total number of states was increasing each time when you added a coin or a die and then reperform the experiment. If you haven't watched the last video yet, don't worry, you can click on the link that'll appear at the top right corner of this video. You can click on that and you can watch the video so that it'll be easier for you to understand what we will be doing in our today's video. So in our today's video, in the second part, we will be discussing about encoding and decoding using coins and dice. But before that, let's just try to explain to you, to those of you who are listening, who are hearing these words, encoding and decoding for the first time, that what does it mean to encode and decode? So encoding is basically a process in which you convert something into another form. So for instance, if there's some sort of a message that you want to send to someone and you don't want any other person to see what's in that message, then what you would do is that you would convert that message to a coded form, a form that is not readable or understandable by any human being, right? And then you'll send that message to the person whom you want to send. And then on the receiver's end, what will happen that the message is then going to be decoded. And decoding is the reverse process of encoding, and it is the process in which that coded form, that coded message will then be converted back to the original message, and like this, they will read what you have actually sent to them. So encoding and decoding is used for secure communications. And an example of this, the best example of this is WhatsApp, right? So when you go to WhatsApp, to any of your WhatsApp chats, you'll see that at the top of the chat, of that particular WhatsApp chat, it's written, you'll read the message that says that this chat is end-to-end encrypted and no one outside this chat, not even WhatsApp, can listen or read your messages. So like this, your communication is secured and no third party can read or listen to what's inside the message, right? So encoding and decoding is important for our secure communications. And in today's video, we will be seeing that how encoding and decoding is done using coins and dice. With the example of coins and dice, we'll try to understand this. And why we want to do this? Because this would actually lead us to a very important conclusion. And so let's get started without wasting your further time, and let me hide my video. Okay, so this is the example with the help of which we'll try to understand that how we can communicate using coins and dice, right? So the situation is described here, and it says that a textile company wants to introduce its latest summer collection in 6 different colors as shown above. So you've got this red, blue, yellow, green, orange, and purple colors here. And this information needs to be shared or communicated to the designers secretly. So now the textile company wants to communicate this information of these 6 colors to the designers secretly. So again, and they would have to use the encoding and decoding concepts to do that. And we'll be using coins and dice for our encoding and decoding purposes. And let's see how we're going to do it. So let's first look at how can we do this with the help of coins. And to do so, let's just first try to understand that how can we use a single coin for communicating, right? Because a single coin is easier to understand. So let's just start with a single coin first. So let's say that instead of those 6 colors, the textile company wants to send information about this red and blue color to the designer. So these are the 2 colors that they want their summer collection to be in. So how could they use a single coin to communicate this information secretly to the designer? So what they're going to, we just saw that a single coin in the previous video, we saw that a single coin has the total of 2 states, right? This is the outcome of the experiment that we did in the last video. So what we're doing in today's video is that we'll be using the outcomes of the experiments that we discussed in the last video and our today's video. So a single coin has a total of 2 states. And what you do is that you say that, let's say I call my red color as the head color, as the head state of the coin, and my blue color as the tail state of the coin. So for instance, when the designer receives their state head, they would immediately come to know that, okay, the company wants to communicate the red color to me. So they would decode this on their part. The decoding process will occur that will enable them to understand that, okay, this is the color that the company wants to communicate. And similarly, if they get the tails, they would understand that, okay, that when this will be decoded, they'll understand, okay, that's the blue color that the company wants to communicate to me. Now, with this single coin, since a single coin has a total of 2 states, as we already know, so in that case, a single coin can only communicate these 2 colors only. It can only represent the 2 colors, or could distinguish between just 2 colors, or could communicate just 2 colors to the designer. And in our current situation, we have 6 colors that we want to communicate, right? So in that case, a single coin is not going to help you, because a single coin can only communicate a maximum of 2 colors. If for instance, there were just a single color here, you would, and there wasn't any blue color, it was just a single color, let's say red color that they wanted to communicate, even then they could use the single coin. Right? How that they could say that, okay, my red state is as head, and the tails represents no color, no information, because there's no other color. So there's just one color, and that's red, right? So a single coin in our current situation cannot be used to communicate all the 6 colors here. Then what do you do in that case? In that case, the company would have to use another coin. And I hope you can distinguish between the shades of these grays. So this very lighter shade of gray here represents the first coin, and slightly darker one represents the state of the second coin. We know that with 2 coins, you have a total of 4 states. And since you have a total of 4 states, so therefore with 2 coins, you'll be able to communicate the colors, 4 different colors, right? But again, as you can see, that with 4 coins, we're still not being able to achieve our goal, because we have a total of 6. We still have this orange and purple here that we want to communicate. So 2 coins is also not helping us. Then what do? Then we need to add another coin. We now need to add 3 coins to do the job. And we know, we already saw in our last video, that 3 coins gives you a total of 2 to the power 3 equals to 8 states, right? A total of 8 states. And now if you take a moment and look over here, you see that with these 3 coins, you have a total of 8 states. So now you have more number of states as compared to the total number of colors that you have. We had just 6 colors, and we have a total of 8 states here, right? So you can like encode or represent these 6 colors using any of the 6 out of 8 states that you have here, right? So there is no particular rule in which you can, or order in which you would like encode them. You could encode these colors in any order you'd like to, but since there are just 6 colors, so you would have like 2 states empty. So what we do here is that now the company says that, okay, so we have got like more states with 3 coins, and we have 2 more states with 3 coins, right? We have got like 6 colors and there's 8 total 8 states. So we have like, we would get like 2 empty states. So, and what they do is that they say that if let's call all tails and all heads as no color, right? So if the designer receives these states, it means that there's no color, right? But if the designer receives any of these 6 states, so then the designer would decode the colors and would then come to know of what color the company wants to communicate, right? So for instance, if the designer like receives this all tails and all heads, so it means the message would then be decoded as no color, right? It's empty, no color. But if they, for instance, like receive this head tail, then this would be decoded on the designer's part as yellow, and they'll come to know, okay, the company wants to communicate this yellow color to me, right? So this is how it's happening. I hope you understand this. So this is how you could use the coins to communicate information. So what we just saw is that a single coin, since it has a total of just 2 states, so therefore it can only communicate a maximum of 2 colors to you. If you have 2 coins that have a total of 4 states, it would only be able to communicate a total of 4 colors. And with 3 coins, you can communicate a maximum of 8 colors, right? But if you had like more than 8 colors, for instance, 15 colors, then of course 3 coins won't be enough. Then in that case, you would have to like make use of 4 coins. So 2 to the power 4 equals to 16 total states you'll get. So then you would use for the states of all the states of the 4 coins to encode those 15 colors, right? So like this, with the increase in number of colors, you would then have to see that how many coins do you need to communicate that information. So this is how you're gonna go. So this is it for the coins part. Now let's move on to the dice part and see that how dice would be used to communicate the list of these 6 colors to the designer. And we know that a single die is a 3-dimensional object that has got like 6 sides, right? So therefore, it will be able to communicate a total of 6 colors to you, right? So now I think you might have already guessed that a single coin would be enough to do the job, right? Because it has got a total of 6 sides, and we have a total of 6 colors. And you could easily like encode these colors as red as 1, blue as 2, yellow as 3, green as 4, orange as 5, purple as 6. So what you've done, for instance, if the company wants to like send this red color to the designer, they were on the company's part, this red color would be encrypted as this 1. So this would be your encrypted message. And this would then be sent to the designer. The designer would receive the message, the encrypted message as 1, and then the decoding process will occur on the designer's part. And this 1 would then be decoded as red, and the designer would come to know that, okay, it's the red color that the company wants to communicate, right? So like this, it's going to go for the case of dice. But now, for instance, if you had like more than 6 colors, let's say 20 colors maybe, then you know you cannot use a single die to communicate those 20 colors. Then you would definitely need to take help of 2 dice at that time. And we know that with 2 dice, you have a total of 6 to the power 2 colors. 2 total states, so 6 to the power 2 total states, so that's equal to 36 total states. So like this, you would be able to like communicate the colors, all those 20 colors, using the 2 dice, the combination of those 2 dice. Right. So with these 2 examples, we reach to some sort of an observation. And this is what we observe while going through these 2 examples. And our observation is that a single coin can communicate less number of colors as compared to a die, right? Why? Because a single coin has only a total of 2 states, whereas a single die has a total of 6 states, right? So therefore, since a coin has got a total of 2 states, therefore it can communicate least a number of colors to the designer. And with this observation, you now reach to a very, very important conclusion. And that conclusion is that the smallest amount of information can be represented or encoded with something that has got 2 states, right? And with 2 states, in our case, a single coin got 2 states, so it could carry the least or the smallest amount of information. Now, amount of information. This is a very interesting way of using the word information, because in our daily conversations, when we're using the word information, we refer this word, we associate this word with knowledge. So you use this word, for instance, in the following way, that I was not informed about this, or if you want further information, please contact Mr. or Ms. XYZ. Or this book will provide you with all the information that you need related to this particular topic. So this is how you use the word information. But when you say amount of information, then in that case, it means that you're trying to use this word information quantitatively, meaning that you now want to measure information. You want to measure the amount of information. So you're using it as a quantity that can be measured. But then how do you measure information, right? So this is how we're talking. So this is how this word information is used in computing quantitatively. So then what is exactly information when you're talking about it in computing, and how do you measure it? Well, this is the question that will be addressed in our next video, in our next part. So in the next part, we will be talking about what exactly is information in computing. And now I think I shall stop the video. I should now end the video. And that's it for today. I hope you enjoyed the video, and I hope you got an idea about what we were talking about and what sort of comparison we were doing today. We were basically, we reached to a conclusion that when you compare coins and dice, when you're encoding and decoding using coins and dice, you reach to this comparison that a coin carries less amount of information as compared to a die that has got more number of states as compared to a coin. So it will definitely carry more information than the coin. So this is the comparison that we made. This is the conclusion that we have reached in our today's video. And this conclusion then with this conclusion, we will proceed with our next part, that is about what is exactly information. And when we will be discussing about this, we would then come to know about what a bit is, right? So thank you so much for watching this video. I hope you guys enjoyed it and you understood what we were talking about. If you still have any further questions, you can ask them in the comment section below. If you have any feedback, any suggestions, you can also write them down in the comment section below. And thank you so much for watching. if you liked the video, please make sure to hit the like button, and please do subscribe the channel, because we like this, the channel will grow, and more people will be educated and will know about quantum computing. And this can only be achieved with your help and support. So thank you so much for watching, and see you soon, and take care of yourself. Goodbye.